So the Richter scale, each number 10 times higher in size and 31 times higher in energy. However, the Richter scale isn't the only way to measure earthquakes. You can also measure earthquakes based off their damage. So if we were to kind of equate Richter scale damage, this is what you would see right here. So a 0 to 3, you might not even feel it. You would only measure either on a seismograph or seeing something shake like a chandelier or a light. A 3 to a 4 would start causing vibrations. Maybe some things would start falling down. A 5 might actually start causing damage to, pieces of your wall. Things would definitely fall down with a 5. 6 through 9 is where buildings start being destroyed. Well-built structures would be damaged with a 6. A lot of structures that aren't earthquake hardened would be very well destroyed with a 7 or an 8. And then only the most earthquake hardened structures like those in Japan and Peru are measured up for a 9. Pretty much everything else will be destroyed by a 9. It's near total destruction. And that's not even including something like a tsunami or fires that may happen after the earthquake. Houses will be brought down, medium-sized apartments will be brought down, most things destroyed with a 9 if it happens directly under your town or nearby. But it's not just the Richter scale. It's also, so with the modified Mercalli scale, if I'm saying that correct, I don't know, it's based on damage, not how strong the earthquake actually is. Now, usually the stronger the earthquake, the more damage it causes, but that's not always the case. It depends. If you have better built buildings, like they do in Japan or Peru or sometimes in California, those better built buildings will actually hold up better against an earthquake, which means they'll get a lower modified Mercalli scale. Now, number 1 on the modified Mercalli is not felt. You don't even feel it. It's not there. Might as well not even exist. You start getting higher, you can start feeling it outside, starts moving things around, difficult to stand. Even though it may be difficult to stand, if you have well-built buildings, there may not be damage to masonry and chimneys. Who knows? And then damage nearly total at 12, yeah, that's basically a magnitude 9 on the Richter scale. So that was the modified Mercalli scale. That was the Richter scale in energy. Where do these earthquakes actually usually happen? Well, convergent boundaries. You've probably heard of the Ring of Fire before. Here it is right here. And as you can see, there is a lot of convergent boundaries in the Pacific Ocean. Here's some right here. Notice a lot of earthquakes. Here's more convergent boundaries, a lot of earthquakes. Here's some over here by South America, a lot of earthquakes. There is some on transform boundaries. So for example, San Andreas Fault in Western United States has a transform boundaries. There's definitely some earthquakes on it, not nearly as much as a convergent boundary. Here's a transform boundary down here by New Zealand. There's a few earthquakes on that as well. There's earthquakes on divergent boundaries, a few of them. They tend to be weaker as well, but they do exist. Like here's a divergent boundary. It has some earthquakes. Here's a divergent boundary by Antarctica. There's a few earthquakes. Same thing over here. Some divergent boundaries and a few earthquakes. But let's be honest, the strongest earthquakes are going to come from convergent boundaries, where the land is literally running up against another land, building up pressure as it sinks under into the mantle. That's going to give you the biggest earthquakes. And in fact, the biggest 3 earthquakes right here, Peru, 9.5, Peru 9.6, Alaska 9.5, convergent boundary, and Japan 9.0, convergent boundary. So convergent, the biggest 3 earthquakes were all convergent boundaries. They do give you the most and the biggest. Now, what about the impacts of earthquake? Well, it depends. Here's the thing about earthquakes. It doesn't really depend, well, okay. How strong they are is not the biggest determinant on how much damage they actually cause. The biggest determinant on how much damage an earthquake causes is where it happens. Actually, yeah, where it happens. That's it. So, for example, this year, 2007, there were 4 magnitude 8 to 9.9 earthquakes. That's a lot of big earthquakes in one year. However, you notice deaths, only about 712 deaths to earthquakes that year. Whereas compare that to something like 2008, notice no major earthquakes, however, 88,000 deaths. If you get a big earthquake in an area that is not prepared for earthquakes, there's going to be way more damage than if something hits like Japan. Japan is ready for earthquakes. Their buildings are built to withstand them. They have early warning seismographs all over the place so that people can take shelter. If you have an earthquake that happens in Sumatra where they're not ready for it and they don't have an early warning system, that's going to cause a lot more damage. So, how strong an earthquake is, yes, that has an effect, but really where it happens and how prepared are humans for it. If possible, we shouldn't be building buildings on San Andreas Fault in California or nearby it. It's not a good idea. But if you have to really build buildings there, at least you can prepare them for an earthquake. It costs more, but it's probably worth it to save lives. Now, why do we care about earthquakes? Well, obviously, earthquakes cause damage, right? Uh, they shake, they can collapse highways, like in this picture. But the damage from the earthquake itself usually isn't the biggest cost in lives or in money. Usually it's fire, natural gas lines breaking, sparks igniting those fire, and gas explosions happening. As you saw in Japan, it wasn't the earthquake that destroyed most things, it was the tsunami destroyed more things in Japan, and that tsunami caused a nuclear meltdown, kind of as well. So you could add that to the list as well. And ground failure, the ground literally collapsing under roads or buildings. So it's not the shaking that does the most damage, it's what's happened after the shaking. Do you have a fire that happens afterward? Does a tsunami come through and destroy things? So, like the 1906 San Francisco fire destroyed most of the buildings. Tsunamis destroyed most of the Japan, or most damage in Japan. The tsunami right here in Alaska as well destroyed a bunch of trees. So remember, it's not always the earthquake. Other things can happen. Now, let's focus on just the earthquake. What if it were just focused on that? Ignore tsunami, ignore fire. What actually brings down buildings? Resonance. When a building shakes, usually each building shakes at a different speed. And you can see that if you have a swing or something like that, you push a swing, the swing goes, it comes back, you push it again, it goes, it comes back. And every time you push it, that swing goes higher and higher. Well, it's the same thing for a building. Every time a seismic wave passes through a building, it shakes the building. If that building matches up perfectly with the resonance of the earthquake, the building will shake, but as it comes back, it gets hit by another seismic wave, so it shakes even more, and then it shakes even more, and then gets hit by another earthquake seismic wave and shakes even more. So certain buildings will actually swing more and more every time an earthquake hits them, and they'll resonate and collapse. Whereas a different building that didn't have resonance won't collapse. And we'll see this coming up here. So just like a swing, or just like anything that you push continuously to make it go higher, same thing can happen with buildings and seismic waves. It just depends. And actually, engineers can use this to help earthquake-proof buildings. Some buildings, they put a giant metal ball in the middle of them to actually stop resonance from happening. The giant metal ball slows down the building so it doesn't match up perfectly